There we go. Okay, thanks everybody for joining tonight. Yeah, let's get started. You all know the name of it, right? Dark Secrets of the Night Sky Photography. I thought that was a good title. And for those of you that don't know me, I'm a retired automotive engineer out of the Detroit suburbs, someone who enjoys all genres of photography, someone that enjoys travel for photography, and someone who really enjoys teaching photography. So travel photography is really my dream job. So thanks for joining me tonight or on YouTube. So when I say night sky photography, what does that make you want to shoot? What do you think about it? Anybody want to give me feedback, or should we just go on? Okay, I'll just keep going. So to me, there's two major areas of astrophotography. First, there's one called wide field, basically a wide angle lens, things like the Milky Way, comets, and stars in general. And secondly, there's the narrow field of astrophotography, focused on planets and nebula and smaller objects, more telephoto or longer range telescopes. So we will focus just on things that are visible with the naked eye, basically, just simple basic camera equipment, no star trackers and that sort of thing. So this is a composite image of the Milky Way from Earth, actually taken in South America by the ESO, European Southern, I can't remember. But anyway, it's way high in the Andes, so it's unhindered by atmosphere and daylight and seasons. So what is the Milky Way? The Milky Way is our galaxy, right? It's one of at least 100 billion galaxies in the known universe. And the Milky Way contains about 100 billion stars, has a width of about 100,000 light years. Really big numbers here. But that'll come into play a little bit later. The thing about the Milky Way is every star we see is in the Milky Way. So any star you see in the night sky is something within the Milky Way. The only naked eye visible object outside the Milky Way is the Andromeda Galaxy, which I think is in this picture right about here. Right about here. So that little smudge right there is the Andromeda Galaxy. So the core, or the center of the Milky Way, where everything spirals around, is the brightest part of the Milky Way. There's dust lanes, there's nebulas, there's a black hole there, all kinds of fun stuff, right? Star clusters are more concentrated in this area. And when most people talk about seeing the Milky Way, they're really just talking about seeing that core of the Milky Way, that most dense, brightest region of the whole galaxy. And then, in case you didn't notice, I put a beanie cap in the corner of the more technical slides that I've included just for completeness. There's no quiz on this. So just kind of fun facts, I think. Every star you see at night is the Milky Way. So I don't think a lot of people realize that. I didn't realize that when I first put this together. So
can I ask you a question? It includes the sun then, right? I had no idea. I didn't know this. So
yeah. The sun is one star in the Milky Way.
Oh,
right?
wow. Cool.
So
Thank you.
here's in
It's
fact, there's
science class.
good segue. Yeah, I'm a nerd. I'm an engineer nerd, so I have to get a lot of background. So here's an overview of the Milky Way itself, right? So the sun is here, and this little spur called the Orion spur of the Sagittarius arm or something. Sagittarius arm, Orion spur. So there's our little galaxy right there, the sun and the planets, orbiting around this core of the Milky Way. And we circle around the whole core. Takes millions of years, but we do circle around it. So the reason for this is not just for the fun facts, but also to show you that in winter, you are here. I forgot to skip that slide, sorry. In winter, the core is not visible because the sun is between the Earth and the core, right? As the Earth orbits around the sun blocks the core. We can't see it in the winter, in our North American winter, I should say, in South American summer. As we orbit around the sun in springtime, the core becomes more visible. It becomes visible just before sunrise, or just before sunrise. because the angle of the Earth's orbit, the best Milky Way opportunities are early in the morning in the spring. So when it first starts coming up in the spring, you need to get up earlier and earlier to get it, just before twilight happens. And we'll talk more about that in a minute. So in summer, the Earth is between the sun and the core, so you basically have all night to observe the core of the Milky Way. However, the nights are shorter here in the northern hemisphere. The southern hemisphere, they're longer, but yeah, so you would get a better view down in the southern hemisphere. And in the fall, the core rises before the sun sets, making for really great opportunities. By the time the sun sets and twilight ends, you have really good views of the core. So it's a really nice time to be getting Milky Way pictures because you don't have to be up at, oh my God, 30 in the morning. So, and then just for another fun fact, the galactic core rises about 2 hours earlier each month, which isn't surprising. 24 hours a day divided by 12 months is 2 hours, right? Or about 27 minutes a week. So, any questions on that one? I should have asked. Bunch of fun facts. So when it comes to being dark, it's not just somebody flipping out the lights, right? It's when it goes from daylight to darkness after sunset. We go through a series of twilights, and these are man-made structures, right? They're just the twilight is just the dimming of the light in the atmosphere. But we name them 3 different levels, so I'll mention those right here. And I'm pulling this from an app called PhotoPills, and you'll see a lot from that app in this presentation. So first we get sunset, right? That's when the disk of the sun drops below the horizon. Of course, in the sunrise is exactly opposite, right? So after all the twilights. So the first twilight is 0 to 6 degrees. Doesn't matter. You don't have to memorize that. But civil twilight is when the sun sinks just below the horizon. Nautical twilight, it sinks even lower. It's defined as 6 to 12 degrees. And then after nautical becomes astronomical twilight, so another 6 degrees down below the horizon. So this is when you really start seeing some stars, is when you get into astronomical twilights. Beyond astronomical twilight is what's called astronomical darkness. So the sun is way below the horizon, the atmosphere is darker, you see more stars, basically. You have full darkness at that point. So it is good to have an app like PhotoPills that tells when the twilight ends. Whoops, I jumped ahead. That's what all this is up here at the top. It tells when these civic, nautical, and astronomical twilights are in the morning and, of course, in the evening. This is all in 24-hour time, just to make things simple. Plus, they're from Europe, so they use 24-hour time there. But it tells you when those things happen, so you can expect when you'll have the most darkness based on an app like this. And then this is an image I made over the twilights, looking west over Lake Michigan from Silver Lake sand dunes. And you can kind of see how the stars fade into view. I kind of like that, how they went from being really dim stars to much brighter stars, because I did a series of long exposures and blended those together. So, any questions on this? You don't need to know the details of the twilights. I just wanted to touch on them. The big thing is waiting for astronomical darkness, right? Waiting till the darkness is really occurring. So it's not a light switch. So engineer, I like a lot of charts. And this slide isn't one to memorize because the times will be different depending on your location, your latitude and your longitude, your location throughout the world. What I do want to show is just the difference in when darkness starts. So in the winter here in Michigan, the darkness may start just before 7 p.m. while in the summer, right, it's just before midnight, about a half hour before midnight. So there's a huge variety in when that actual darkness occurs. And of course, same for the twilights too, right? Twilight is about 3:47 in the morning is when that first nautical twilight starts. So there's not a lot of time to see the sky at night. Yeah. So as I mentioned in earlier slides, the Milky Way core rises and sets just like the sun, just like the moon, all those things, right? Because the Earth rotates and brings it into view. It's just the Earth is in different positions around the sun to make it visible at different times. So what's interesting about this is early in the spring, the core just starts to rise early in the morning, but the core visible end matches up with the twilight, right? So it's the light of day that's actually ending the visibility of the core. But as we get, throughout the months of the year, you get more and more visibility as you go through. So it's earlier and earlier every night. It's longer and longer each night, the visibility. Until you get in the fall when it's the opposite. It's the darkness that's blocking the light to see the core of the Milky Way. So it kind of gives you a visual, I think, of the Milky Way is visible at early in the morning in the springtime and early in the evening, early at night in the fall. So, and this just gives you an idea of how many hours are visible. But it starts early, so you really don't have to start out at night. So even though the nights are shorter, it still gives you the longest time visible for the Milky Way in mid-June and July. At least here in Michigan, anyway, where I live in Michigan. But you can go out anytime. Just picking a time here. So here's one night when darkness starts at 2318 and the visible is at 2318. So it's visible the entire night. So while the Milky Way is visible in early spring, the angle of the galaxy is best for taking Milky Way arch photos in the spring, which I'll talk about later. And in the fall, the Milky Way is visible right after twilight. So it's possible to get the shot and still go back to bed at a decent hour. That's what I like. So the angle of the Milky Way changes throughout the year. It's more of a sharper angle. It's lower in the sky in the spring, but then it's higher in the sky in the fall. So there is a little difference in how the angle of it appears to the horizon too. Any questions on this? A lot of data, but really just need the visual of how it changes from an early morning thing to an early night thing as the year progresses. And then December, January, not much visible at all, except the other stars in the Milky Way. For planning of where to see the Milky Way, I use an app, as I mentioned before, called PhotoPills. And if you're interested, I plan to have a presentation on PhotoPills sometime in the near future. So this app is designed to have quote unquote pills or solutions to your photographic headaches, hence the name PhotoPills. So I won't go into detail of this, but what you do here is you basically go into the planner. It opens up another screen. It'll show you when the galactic core is visible. So visibility of the GC or galactic core. It'll tell you which direction it's visible, where it rises and sets, and how it looks in the arch in the sky. That's what this dotted line is. So it's a really powerful app. It takes a little time to learn how to use it, but it's really nice. It'll also tell you the elevation, which is the angle it is to the horizon, which is nice, and the azimuth, which is the direction. So nice thing about PhotoPills, it also has what's called a night AR or augmented reality mode. So I could go to a place that I'm planning to shoot the Milky Way in the daytime, and I could plan for that shot at night just by setting the time to be that night. You can see I set this one to be 9:16 p.m. Oh gosh, I first did this 5 years ago. And then I just visualized where the Milky Way would be at 9:16 p.m. on 9/6/21, right? So I just held my phone up and it overlaid on the foreground. It overlaid where the Milky Way and where the core would be. It's really a powerful app. It's got a lot of nice, great tools in it. And it's like $10. It's not that expensive. And then here's the shot I took later that night, right? So I went back later that night and there's the Milky Way pretty much just as it predicted. You can see these legs right here of the dark horse are right here as well. So the galactic core is kind of right in here, this area. So it's a great planning app. Hopefully you can join me later in the year when I have that presentation. How to find dark sky. This seems kind of obvious, but there's a lot of science into finding dark skies, which being an engineer, I'll go into. So what affects the dark sky? Lights on the ground reflect back up into the atmosphere, which then reflect back down in the atmosphere once they reflect off dust and moisture and whatever in the air. And it just creates an area that is brighter than the stars behind it. So when that light goes up, it reflects off those items, those things in the sky, all those particles. And if it's brighter than the stars behind it, you won't be able to see the stars. So there are many, many light sources. If you look at the ground lighting at places where they are certified dark sky locations, you'll see they have covers or shields that basically protect the light from try to protect the light from going upward. And so it's only projected downwards, are also a little bit dimmer, so they don't get as much reflection up in the atmosphere. So, and then the moon has a lot of effect on dark skies as well. And of course, the moon goes through cycles. A little bit of moonlight is nice to have, as it can help illuminate the background in a night sky photography shot. Yeah, stuck. Okay. So quick introduction again, you don't have to know the details, just a couple things on this, but I'll run through it. Again, it has that little beanie cap in the upper right. So to quantify the brightness to the ground, astronomers have created a 9-step scale to determine how dark a location is. It goes from 9 being the brightest location, stars are basically invisible on the left side, to 2 or 1 being the most clear to see stars. So generally for Milky Way photos, 4 or less is what you want on this Bortle scale, as it's called. Yeah, so again, not important to know the details, but just the 4 or less on the Bortle scale is all you really need to know. And then here's a dark sky map of the United States. These are available all over the web, but it's not the same scale as the Bortle scale, but it clearly shows where all the urban areas are to avoid. And with this map, you can really see that line along the center of the United States where the population changes, right? From the shadow, the area doesn't get as much rain from the Rocky Mountains eastward. And then it starts picking up again. The rain starts picking up again from rain from the Gulf. So, but even with these bright areas, there are still pockets where you can view the Milky Way. So you may be in a really bright area. Michigan looks really bad here, but let's zoom into it. So here is the state of Michigan, my home state, with a list of dark sky parks and preserves. And behind each one of these letters that labels each one of these, I put the Bortle classification for each one of these. So, 2s, 3s, and 4s, they're all pretty good as far as astrophotography, or appear good anyway. Even these 4s down at the Ohio border, aren't that terrible, Ohio-Indiana border. While the darker skies are closer to the Great Lakes, right? Like Huron up here, 2s and 3s, out here in Lake Michigan area, and way up here in Lake Superior is a 2 as well. I'm surprised this Beaver Island is only a 2. That's a really dark area, pretty far from all the city lights. So you may have to, with the dark skies, they're really nice for dark skies, but the thing is, there's not always a good foreground to take a picture. So a great composition is going to have something in the foreground and the Milky Way in the background. So you don't just want the Milky Way, you want something in the foreground. With those dark sky parks, it's not always evident that there's something available to use for a foreground. You can search around for a tree or a boat or a pond or something, or a picnic table, whatever, to put in the foreground. So again, here's that map of Michigan, a little wider shot, I guess, but it shows both Lake Huron on the right and Lake Michigan on the left. If we look closely at this map, even though it looks really busy, really bright, if you look really closely, you can find some very small areas that are really low Bortle class. Here's one on the west coast on the Lake Michigan side that's Bortle 3. Here's one up in the Thumb area that's Bortle 2, 3. Pretty dark area. There's a lot of darkness around this area, which is really nice. That's about 3.5, 4 hours from my house. Actually, they're almost equidistant. They're almost the same. So, but these are my favorites. So, did I not? I thought I had. Okay. Oh yeah, these are the pictures from that place. Okay. So on the left is Little Sable Lighthouse on the shore of Lake Michigan. That orange glow you see above the horizon is the cities of Milwaukee and Chicago, probably 60 or so miles away across Lake Michigan. So it's amazing how much those cities really affect how far that light comes from those cities. But nice foreground, and I have this little Sable Light and the nice Milky Way in the background. The one on the right is in the thumb area of Michigan in Lake Huron. This is Point Aux Barques Lighthouse. Looking at a direction early in the morning across toward Ontario, kind of a lowly populated area of Ontario. So, yeah, Ontario, Canada, for you guys in California, in the distance. So really nice skies all the way to the horizon there, even though the cities are closer or towns are closer. But don't let the lack of dark skies stop you. Even in the city, there might be enough darkness to catch a star or two. These two images are from within the city of Detroit. Photo on left is the Michigan Central Railroad train station. It's an old image. It's before Ford renovated the building. But I actually caught a comet over here, just left of the station. Yeah, not quite the shot I wanted, but I did capture both of them in one picture. And the one on the right is the conservatory on Belle Isle, the river in the Detroit River between Detroit and Windsor, Ontario. You won't see the Milky Way core in the city, but you can see some stars. So I saw that even in Boston in the workshop I did there last year. We did some night shots at a plaza, but up in the sky you can see little specks of light that I caught with that long exposure. So long enough exposure, you will capture some light in the sky. Not out of the realm of possibilities. So what makes for a great Milky Way location? As we talked about already, Bortle 4 or less. Lower is better, right? Lower is darker skies. Another thing you want to look for is dark skies, but mostly dark skies to the south. South, southeast, really depending on where the Milky Way is going to be. And the reason is because the Milky Way intersects the horizon in the south. So if you have a bright city like Detroit right to your south, you may not get a good shot to the south because of the dome of light that's coming out of the city. So dark skies to the south is really important. As I said before, a foreground subject to the south again, right, toward the Milky Way is always good to have. And then a place away from cars, roads, and people with flashlights. So we had that problem in Moab trying to get some shots at night, and there were so many cars coming in and out that we couldn't get a decent shot because there's so many cars passing on the road, which kind of surprised us. So based on that description, which location would you choose, right? A, B, C, or D? This happens to be the bright city of Detroit and Lansing and Jackson, Michigan. So A has that dome of light south of Detroit, so that's probably not so good. B has Lansing directly south of it, probably not a good shot. C doesn't look too bad. You're kind of splitting the gap here between Ann Arbor and Jackson. D looks not too bad because you have nothing directly south, just boring old Ohio. Nothing offense, Ohio. But so here's a shot from location C, right? You saw this one before, and you can see on the left is Ann Arbor, on the right is Jackson, Michigan. And I'm shooting basically right between those two cities. But again, it's amazing how distant those cities are and how much light reflects back through the atmosphere. But if you have really dark skies and a fast enough lens, you can capture some really wonderful things. This was in Namibia, where there are some deeply dark skies. Although this night we had a few clouds, but this is the southern Milky Way, or Milky Way from the south, from the southern hemisphere, I should say. So we're able to see things in this that I'm not able to see north of the equator. So including these large and small Magellanic clouds, basically many failed galaxies, but still within the Milky Way, or within the influence of the Milky Way anyway. And filling the frames with Milky Way images is nice, but it's even nicer to have a foreground. These are both from Namibia as well. I mean, just exceptionally dark skies. Yeah, the one on the left was taken right from my my hut Just went out the back door and stood on the deck and shot that picture overnight. It was just so beautiful and so bright. The only problem there is just a little bit of orange dust in the sky, but from the desert. But yeah, just amazingly dark skies. How to find a clear sky. Again, something that seems obvious, but I'm just going to science the heck out of it. So for clear skies, don't try to read this whole thing yet, but for clear skies, I use a website that's called clearoutside.com, or they have an app that's called Clear Outside, simply Clear Outside. It's free. And the app does everything I need for planning. So it tells me the cloud forecast, it tells me the phase of the moon, it tells me the times for astronomical darkness, and they're all distilled into one page and a week out. And best part is it's free, right? So it's a bit of learning to how to use this app, but let's go through it real quick and I'll show you what it's about. So once you pick a location, this happens to be up in the thumb of Michigan. You can put in locations, it knows locations, or you can put in the GPS coordinates. It'll tell you what the Bortle class for that location is. So again, this is that point up in the thumb of Michigan, one of the lighthouses, one of my favorite lighthouses. And then you have all this detail information repeated throughout a week's forecast. So all the data is there about moon phase. It'll tell you the day of the week, obviously. All the dates there about moon phase, the percent full, when it rises, when it sets, what phase it's in, all those sorts of things. So it's all just kind of summarized in one place. This colored scale right here tells you what the cloud cover is going to be like. It's a simple red, yellow, green, right? So green is good. Green means there's no cloud cover. So we're looking for areas that have green. I just like how simple this is. The second line down is the sun line. So this shows those areas of darkness and twilight that we talked about earlier and when the sun is up. So for this one, you're looking for astronomical darkness, which in this graph is black. And then the bottom line is the moon phase. So even though the moon is 77%, a pretty full moon, it doesn't rise until later. So you've got a little gap right here where it's still dark, right? Black skies, green clouds, and blue for the moon. So three colors you're looking for: green for the skies, black for the sun, and then blue for the moon. And you get all three of those. You get about 3 hours of that right here, right? So all three of them together before the moon rises. And that's really the holy grail of astrophotography. No clouds, no sun, and no moon, right? Those three things. And it's all there on this app. It's all a week in advance, right? It'll all be there together. So you can look at a chart like this. Once you know those little details and get used to it, you can start looking for areas which look possible for doing the night sky. Of course, any forecast is going to be worse further out you go, but even though this is still 39% moon, right? Still a pretty full moon. It doesn't rise. It gives you enough window to still shoot it. This time for about 2 hours, 2+ hours. Here for about 3 hours. Here for about 4 hours, and here almost 5 hours. After that, things aren't looking so good. So probably not so good. So I love this app in its simplicity. I just got to look for three colors and I'm good to go. Any questions on that? Not something you have to use, but I'm just telling you why I enjoy it. So that's all the background done. Finally, we can start talking about taking pictures of the Milky Way. Finally get to the camera settings. Let's get into it. The first thing I'm going to say is know your camera, right? And I mean intimately. You need to be able to find anything on your camera in the dark. You should know your controls with your eyes closed because you will be setting them in the dark. So all these things you need to know how to do in the dark, assuming you're setting up in the dark. I would always recommend the first times you go out to set up in the daylight and then wait for it to get dark so that you're all set. Get your settings in your camera right, everything except focus, obviously. You want to be in manual mode. You want to be in manual focus. I like to turn auto white balance off because white balance can change from image to image. Even though the light hasn't changed, it can actually change from image to image, which is a real pain. You just have to reset it in Lightroom. It's not that hard, but it's still a pain to remember to do that in Lightroom. Turn your screens down on your camera. In fact, turn the back screen off if you can, so it doesn't disturb other people. Focus peaking is not much help in focusing on stars. We'll talk about that in a minute. And then just know the three settings, right? ISO, aperture, and shutter speed. You got to know those cold. You got to be able to set those in manual mode. And you want to be able to do an image review with histogram. That's something you probably want to learn how to do at home before you go out in the field, so you're not struggling with your camera trying to find where the image review histogram is. Not so bad in Sony, but I know for like Canon, it's a little more difficult to find. Nikon, it's not so bad. So, and then finally, changing batteries. For sure, you got to be able to change batteries in the dark, because when things get cold, batteries get cold, they don't last as long. And one final thing to remember is try not to use a bright light. Setting up in the dark allows your eyes to become dark adapted for night vision. But any bright light is going to ruin that dark adaptation, so you're not going to be able to see things as well. And dark adaptation takes 15, 20, 30 minutes, depending on your eyes. So, and you don't want to be that guy, especially with a group, with the headlamp flashing it at everybody, blinding them. Others will lose their dark vision. A really dim flashlight is the best. Red flashlight, if you have it, is best. So dim as possible setting, but best if you don't use a light at all. But if you have to, you have to. There are always things, right? So, okay. Now for focusing. Focusing is one of the hardest things to do with night sky stars. Autofocus generally doesn't work. Some of the newer cameras are getting better at it, but it generally doesn't work. It's really hard to do. Most modern cameras can't focus on the stars yet. So what you need to do is, of course, turn off autofocus and then turn your lens toward the infinity setting. So if you can turn the focus already toward infinity, you'll be very close to focusing on the stars. You don't want to be at the closest setting, because then the stars will be deeply out of focus and you won't be able to find them. So you want to be close to, if you can, to finding the stars. Preferable not to use the back screen because it creates light for others, especially if others are taking pictures. It's surprising how little light it takes to ruin a picture, a night sky picture, and the back screen is definitely bright enough to ruin people's pictures. It's just amazing how little light it takes, because you're taking long exposures, right? You're taking 15, 20-second exposures with the aperture wide open, with the ISO cranked up. So your camera is very sensitive to light. Any little amount of stray light can ruin a 15-second exposure. So once you're on, you're viewing the live view hopefully through your electronic viewfinder, point toward any star, the brightest star you can see. Doesn't have to be on a tripod. You can be doing this handheld, right? Doesn't matter which star, because all the stars are about the same distance away as far as the camera is concerned. Another hard one is to zoom in digitally. With Nikon, it's the magnifying glass. You can zoom into the live image on some of the electronic viewfinders. Yeah, with Canon, I'm not sure where it is. I got my Sony set up so that I can just push a button and it zooms in automatically. So it's another thing to make sure you know where that is. And you zoom in digitally. You don't zoom in with the lens, right? If you zoom in the lens and then zoom back out, you've lost your focus. So you want to be at the zoom range that you will be shooting the picture at, and then zoom in digitally, zoom in electronically on the live view. And then focus on the star while it's enlarged. The star will look like a point of light, hopefully. If it doesn't, just turn your focus knob until it does. As you go beyond focus for the star, it'll kind of turn into a bright donut, kind of get a halo and then turn to a donut that's out of focus. And then you'll go through a sharp focus where it narrows down again. and then back the other direction, it'll start opening back up into a donut again. So just move it back and forth until you get the smallest star possible, right? You want it to be a sharp point of light. And again, once you've got focus, don't touch it. Again, any stars you shoot throughout the night, all that focus will always be the same, right? Your camera doesn't know the difference between 100 light years and 125 light years, right? It doesn't know the difference. But if you bump it or touch it, you will have to refocus, which is a bit of a pain. And always good to do a test shot. Oops, I think I skipped one there. Always good to do a test shot and zoom into the image to review it to confirm that you have focus, to make sure that the stars are sharp, especially in the center of the lens. Yeah, if you're zooming into a star, I should say that you want to do that in the middle of the lens if possible, somewhere in the middle, which is why you can do it handheld, right? Once you set it up on the tripod, then you're good to go. It is one of the hardest things, but a couple things you'll have to look up for your specific camera model before you head out and practice. If you can't find a bright light, zoom in on a cell tower or something that's as distant as possible and just hope for the best. Ideally, you'll be doing it to a star or something very bright. So really briefly, I want to talk about the exposure triangle. This is going to be real brief because I don't like the exposure triangle. The thing I don't like about it is it doesn't show the relationship between how one setting affects the others, right? If I raise the shutter speed, how does that affect the ISO and the aperture on this? I don't know, right? It doesn't tell me that. So I've kind of worked on something that I call a balanced exposure. Moving any of these settings, aperture, shutter, or ISO to the right, adds more light to the image. Moving them to the left reduces the light in the image. So, and the histogram below that tells me I currently have a balanced exposure. How do I know that? It's because this graph is not crushed onto the left or overexposed onto the right. So it's all within those two goalposts. That's a good thing with a histogram, is to be within those two goalposts. So let me back up a little bit and just talk about histograms for a second. This is a simple little demonstration I came with, or I developed just for histograms. It's a little, let's consider this to be a 3x5 image. It's a very small image. This is a really cheap camera. It's only got 15 pixels, right? And it's only black and white. So you can see the pixels have 4 different tonal ranges, from white to low gray to high gray to black, 4 colors, right? And if I create a graph that has each one of those colors and count the pixels of each color, I will create a histogram. So first the black color on the left, there's 3 of the black, there's 4 or 5 of the dark gray, there's 4 of the light gray, and then there's 3 of the white, right? So I've got a little histogram graph right now, right? And it fits within our graph and it doesn't crash into the left side or the right side. So it's a good histogram. Now, if I take that same histogram and I overexpose it, if I brighten it too much, and then, so this is our little camera here on the left side, and then I recount the pixels. So what was black is now dark gray right here. What was dark gray is now light gray, and what was light gray is now in the whites, right? Where it was light gray before, it's now in whites, which means there's a complete loss of detail between the whites and what was light gray. That means that's what's meant by you're blowing out the whites, right? Things that did have contrast before suddenly don't have tonal contrast, right? So, and the same thing on the left side, right? If we darken the image, all the pixels shift to the left, right? What was white becomes light gray. What was light gray becomes dark gray. What was dark gray becomes black. So piling up all the blackest tones, this is known as clipping the black tones, right? Or the darks of the image. So with that out of the way, let's look at a night sky image, right? So here's a histogram for this picture on the left. This is up in Sleeping Bear Dunes National Park, up in the dunes off Lake Michigan, a famous barn that's up there. And again, we want to make sure that when we expose that this histogram is between those two sides, right? Between those two guardrails or goalposts, if you will. So where are these darkest tones coming from? These first little humps? Those are coming from these trees, right? These darkest areas. It's just basically counting all these dark pixels and putting them there on the graph. The largest hump is coming from probably from the sky, right? It's the largest area of the picture. It's dark area of the picture. There's a good range of tonal ranges. It's a good range of tones in that image or that area. So darkest area to lightest area could all be that sky right there. And then we have this little low area, right? So what's all that? Those are the stars, right? Those are the brightest parts of the image, which happen to be the stars. They're really low because the pixel count is low for all of those little points of light, right? But they're all brighter than everything that's on the left. So this is good. I'm between the goalposts. I don't have, not blowing out the whites, and I'm not crushing the dark tones as well.
Scott, where were you getting the light from to the south of the barn?
Yeah, I don't remember. Some town to the south. I don't know.
It's just a town. Okay.
Yeah,
Thank you.
yeah. Most likely. I mean, generally you see light on the horizon. That's what that's going to be. So, and then the low clouds don't help, right? That just helps. It's like a screen for that light to help project that light. So back to our balanced exposure graphics. So what happens if I open the aperture 2 stops to gain more light, right? Which is what you want in night sky. You want as much aperture as possible to gather as much light as possible. So if I move the aperture to the right, then I start crushing these white colors or blowing out these white colors, right? The exposure becomes unbalanced and the histogram gets crushed up to the right side. So what do I do to counteract that? I can reduce the shutter time. If I'm 2 stops to the right for one and 2 stops to the left for the other, it all balances out again, right? Add 2 here, take away 2 there. It all balances again. So now I have a balanced exposure again. Another way to approach it would be to change the ISO 2 stops as well, right? Doesn't matter, one or the other. They're all trade-offs actually. I could even choose to do one each direction, right? So one lower on the shutter time and one lower on the ISO. So they're all balanced exposures. Each one's a little bit different. So I don't know. Hopefully that helps. I think it's a little better than the exposure triangle, and then it shows that interrelationship of how the 3 camera settings work together. So how do we set the shutter time for night sky? Unfortunately, it's going to take some math, and we'll have to go through it. But you don't have to memorize all this, but it's good to know. For full frame cameras, the general rule of thumb today is about 400. Divide 400 by the focal length of the lens. In the days of film, it used to be a 500 rule, but cameras have gotten better over the years. So if you had a 12 millimeter lens, 400 divided by 12 comes about 33 seconds. So you round down to 30 seconds. Your exposure with a 12 millimeter lens, you'd start at 30 seconds. And then you would check the exposure, check the stars, that sort of thing, make sure there's no movement. Similarly, for a 16 millimeter lens, let's say I have a 16 to 35 lens, I'm at 16 millimeters, 400 divided by 16 is about 25, so 25 seconds. So as you can see, as the focal length goes up, that the shutter time goes down. That same 16 to 35 lens, if I put it at 35 millimeters, that drops down to about 10 seconds, right? Something less than 11.4 seconds. So again, longer focal lengths allow for less time for the exposure. And really the reason that is the more zoomed in you are, even though these are all wide angle lenses, the more you can detect the movement of the stars, right? Or technically the rotation of the Earth, but it really exaggerates as you zoom in more and more. When I was using the 135 millimeter lens to do some night sky pictures, my individual shots were less than a second. So, but I stacked a bunch of them, so to gather more light. So crop sensor, you can just convert to full frame equivalents. Basically, you're dividing that same number. You can divide that 11 seconds or 25 seconds or whatever by your crop factor or whatever that is, 1.4, 1.6, whatever. It's just more math. And then if you have a really high megapixel camera, you might want to go even shorter because of the higher pixel density. So if you have a 60 megapixel camera, you might want to go a little bit shorter because the number of pixels, the close proximity of all those pixels, or pixel pitch as it's called, will detect the movement of the stars faster than something that's only 24 megapixels or 30 megapixels, half of that. So something to think about, but yeah, it's really when you review the image, you'll be able to, whether you'll be able to see the movement of the stars or not. And then just for reference, star shutter times can be longer if you're shooting to the north, because there's less movement to the north than there is at the celestial equator. We'll show a little bit about that in a second. And then shutter time will be shorter for things that are at the celestial equator. Now everybody's going to say, what the heck's the celestial equator, right? So you can see the movement in this star trails image, right? So as we get closer to the pole, the North Star, if you will, there's less movement in the stars, right? Because you're actually looking at the rotation of the Earth. But as you get closer to the equator in the sky, the celestial equator, there's a lot more movement, right? So as you get closer to looking at the things that are directly overhead here in the northern hemisphere, things will appear to move faster. So again, all things in consideration, but generally not things you have to worry about too much. The simpler way to calculate shutter times is to use my friend PhotoPills. They have a pill in here that's called Spot Stars. And really what that does is it freezes the stars. In this pill, you set your camera model, you set your focal length, you set the aperture, and then the angle from the celestial equator. You can play with that if you want to. I just leave it at 0. And then you can go really fine on the or default or maximum, I guess. But I just leave it at default. So it calculates 2 different shutter times. It's a little bit confusing. One uses the old 500 rule, right? So 500 divided by the focal length. The other one uses a really advanced calculation developed by the French called NPF, and stands for aperture, P is pixel, and F is focal length. So it takes into account the megapixels of your camera, the aperture, the focal length, all these optical calculations, and spits out a number. Long and short of it, I use somewhere in between the two. But it's a great thing to throw in your information. It spits out a number. You don't have to do any calculations. You don't have to remember if you got a crop sensor or whatever. It's really, really easy to use. So, like I said, you can select the celestial latitude if you want, and it changes the numbers. I just want to show you that, but I never use it. I always keep it in the more conservative 0 degrees. And then as you change focal length, the numbers change as well, right? So they get shorter for the longer focal length. And again, I just shoot somewhere in between. And again, that's just a test shot. So I always go back and check my first test shots to make sure that the stars are spot stars or stationary stars. I don't trust that I can go home without checking that first. So we've talked about shutter time. Now let's briefly talk about aperture. In photography, aperture is what controls the amount of light that touches the sensor or comes through the lens. Each one of these steps in the aperture is called a stop. And a stop just means that it's doubling the amount of light, or halving, depending on which direction you're going, through the aperture. So in astrophotos, you want to gather as much light as possible by having as much aperture as possible. And the way that f-stop works, the largest opening is the smallest number because it's a ratio. So f1.4 is double the area of f2.0. So you're gathering twice as much light from f1.4 to f2.0. So it's pretty big deal. It doesn't look like much, but it's a big deal. Because you can half your exposure, or you can half your ISO just by using that wider, faster lens. The downside to wide open apertures is that sometimes there are optical flaws that appear when you're at the limit of the lens's capabilities. So If you're choosing an astro lens, I can highly recommend you always investigate how it's graded as far as an astro lens. And also the widest opening, which has the shallowest depth of field, right, on the left side, the one that gathers the most light, has the shallowest depth of field. It can make the foreground out of focus if you're focused on distant stars. So you may have to take two pictures, one of the foreground, one of the stars, and then blend those together if you've got a really shallow depth of field and the foreground is close. But usually it's acceptable, but it really, if you don't have things too close, it's not too bad. So this part gets a little nerdy again. This is 4 shots with the same lens, and I just wanted to test what the different apertures affected, how that affected the stars in the lens. And so upper left is f2, lower left is f2.8, upper right f4, lower right f5.6. And if we look closely, there's some darker corners. This is just the very corner of the image, the upper left corner of the image. So you can see that upper left corner is getting darker here and here, right? This is vignetting that's caused by having the wide open aperture. And also the corners show a little bit of distortion called aberrations. Each lens has its own performance at largest apertures, so your mileage may vary. Some people recommend stopping down a stop or two on the fastest lenses to improve performance. I say the only people looking in the far corners of your image are photographers, and I don't care about them. The general public won't notice any minor issues in the corners unless they're really bad. But these are the kind of things you want to look for in a lens, is that it doesn't have as much vignetting or as much, or at least correctable. And then the big thing is aberrations. You don't want a lot of distortion. This f1.4 50 millimeter lens I basically had little seagulls in the corner of every picture because it was so bad with aberrations. But it was a cheap lens. So lesson learned. So now we need more light in our image. We've already talked about aperture and shutter time being as long as they can go, right? Can't go any lower or wider on aperture, can't go any longer on shutter time, or we start to blur the stars. So what's our only choice to change? Hopefully you said ISO. ISO is the bane of many photographers. The ones that venture into the high ISO because of the dreaded noise monsters that lurk there. Let me show you how to tame those noise monsters. So for night photography, you're pretty well set on aperture and ISO, or aperture and shutter, excuse me. ISO is the main control for night photography. Raise your ISO, basically I start at 1600 and then just raise the ISO with test shots until that histogram pulls away from the left side. So I'm not all blocked up in the dark shadows. Generally, you don't have to worry about the right side of the histogram for stars because the scene is generally dark. It's really just trying to get that detail in the shadows. And then higher f-stop lenses or longer focal length lenses require higher ISO and potentially more noise. So if your lens only goes down to f5.6, you know, again, the doubling, right? So f4, f2.8, f2, right? There's a lot of light that's being lost because of that minimum aperture, or maximum aperture, sorry, minimum number. So let's talk about the noise monster a little bit. This is a slide I put together just to show something called ISO invariance, or the ISO doesn't really matter a lot, but it does matter a little bit. Anyway, this is 14 images ranging from 560 ISO up to 51,000 ISO, right? All we're taking at f2, all we're taking it at 15 seconds, all with the same lens. So, and a pretty good astro lens too, not that bad. And I just combined them all into one image just to see what it looked like. To me, it's until you get to this middle line right here, it's not really easy to tell there's a difference, right? And even to the right of this line, it's just a little brighter. It's not like there's no detail. There's still lots of color in the stars. There's blues, there's yellows. It's just a little brighter. But believe it or not, that's ISO 12,800, right? All the way up to 51,000 in the lower right corner. So don't be scared of ISO, right? I'd rather have a proper exposure at the proper ISO than have something underexposed that I have to brighten up later. You don't want to have to brighten your image later, especially with astrophotography. In general, you don't either, but don't be afraid of ISO. I know we've all said there's monsters that lurk there, but it's not something to be afraid of. So these are the corresponding histograms for each one of those ISO settings. And what I try to do in night sky images, I raise the ISO until the major peak of the shadows is about a third of the way across the histogram scale. Remember, there's no single setting for night sky just because there's no single night sky. Sometimes the sky will be brighter, sometimes it'll be darker, there'll be different Bortle numbers of locations you're at, there'll be different cities to your south. Sometimes the ISO will be lower and sometimes it'll be higher. So ISO will be higher when there's bright lights. It's kind of counterintuitive. ISO will be lower when it's bright lights, excuse me. So if I'm in the city, I'm going to shoot at a lighter ISO, otherwise the picture is going to be blown out. But if I'm in the darkest skies of Namibia, my ISO is going to be a lot higher, trying to pull out that detail in the shadows. But again, it's not something to be afraid about because you're gathering a lot more light in those darker areas. You can always darken it, but you can't brighten it later. So for this particular set, I would choose probably ISO 6400, maybe 9000, which may scare some people, but that's a typical night sky image. You want to be about a third of the way across for that major dark sky area. And again, this is the black sky, right? That's what most of this is. And then all your little stars are down here on the right. Here's another comparison with a Sony camera. Similar test, just with a new camera, different lens too, a Sigma f2.8 lens. I've since got an f1.4 lens, but we'll talk about that later. But again, I would choose one that's about a third of the way across. You can see at ISO 102,000, the brights were all blocked, and when I tried to pull the detail back, it just wasn't there. And there's kind of a graying here at 51,000 as well. So again, I would pick one that's about a third of the way across for this particular place, which happened to be a brighter area. That's that area between Lansing and Ann Arbor. It was about ISO 1600 to get the Milky Way, but I got some pretty good detail there. I wouldn't go any higher because then I'll start losing the detail in the stars. And I wouldn't get any lower because then I'll be losing the shadows area. So I would probably be in the 1600, maybe 3000, somewhere between these two. So I told you I'd tell you how to combat those terrible noise monsters once you've taken those high ISO pictures. One way to combat noise is to get a faster lens, right? Like I said, an f2 lens, f1.8 lens, f1.4 lens, they gather a lot more light and have options to snap down to minimize distortion. Be sure you look at reviews for lenses and see if you can find reviews that talk about how that lens works for astrophotography, because aberrations are a real problem with certain lenses. So I'm using the Sigma 14mm f1.4 lens now, which I'll talk about later. Another method to combat noise reduction is something called image stacking, where multiple images, you may take 10 or 20 images and you'll stack them together and they'll be blended together by software. And what that software does is if there's a star in all 10 images, that star will carry through. But if there's noise outside of that star, it will average that noise out so that it disappears. Usually, like I say, 10 to 20 images are common because they're fairly short exposures, typically 10 to 15 seconds. And there's software both for Mac and for PC as well. I have a Mac, so I use Starry Landscape Stacker, and it does an excellent job. It does a great job. All the images you see processed here were with Starry Landscape Stacker. So another way to combat is by multi-image panoramas. You can do that in Lightroom. You can do that in Photoshop. If it gets really complex, you may have to buy panorama software called like P2 GUI, which is like top of the line in panorama software. But for me, Lightroom has worked just fine. And I'll show some examples of that later. Oh, so panoramas, I didn't mention that. Basically what a panorama does is it makes the image bigger and bigger, right? Bigger than the sensor size because you're blending together multiple images. And then when you compress that back down to like normal size, the noise gets so small that you can't see it anymore. So it kind of filters it out by just compressing the image, downscaling, they call it. The image, kind of the opposite of what Gigapixel and those sort of software do to enlarge images. This is the opposite. So it reduces noise by making the image smaller. You can also use denoise software, Lightroom, Photoshop, Topaz Denoise, whatever. Just be careful it doesn't take out the stars too. Stars are little points of light which look like noise, but they aren't. So it can take out some of the smaller and lighter stars and kind of sanitize the image a bit much if you try too heavy on that. You could try to use ISO noise reduction through an old process called subtracting dark frames. Oh, I've got two things here, sorry. You can use high ISO noise reduction in your camera, so you can leave that on so it takes a second picture and subtracts an image from your first image. So basically what it does is it takes your normal light image and then it takes another image without any light to it and it subtracts one from the other. So the second image is has a picture of the noise, basically. And you can do that in Photoshop as well by just, after you take your astrophoto, you take a picture with your lens cap on, and you'll basically take a picture of the noise, and then you can subtract that later in Photoshop, subtract one picture from the other. It's kind of an older technique, but it's a possibility. It takes out the noise that's always there, so like stuck pixels or whatever you have in your sensor. But if the noise goes up and down, it's variable, it doesn't take that out because the dark frames don't necessarily pick that up. Anyway, it's used a lot more in astrophotography. So a couple demonstrations here. This is an image of, or a demonstration, an example, excuse me. This is an example of image stacking. The one frame on the left, single frame, and on the right, 20 images stacked. For this resolution and through the zoom, you probably won't see much difference. So let's take one little area of this and expand it to show a little better. And hopefully you can see the noise that's in the left-hand frame, in that single frame. And the right-hand frame, that noise is all gone. It doesn't focus the image anymore, but it gets rid of all that noise between the stars. So you end up with being able to see a lot of the lighter, finer stars a lot better, and they aren't buried in the noise. I'll go further. Yeah, I zoomed in even further, I forgot. Yeah, again, it doesn't refocus the image, but it eliminates that noise between the stars. So it's really a great way to go because it just averages that out. And it's software. It's pretty easy to use. Similarly, here's a comet stacked. This is a bunch of 1 second images, again with a 600 millimeter lens. 1 second, this is a single image on the left and then multiple images on the right. That's the first time I tried it, so it's a little bit noisy still. The processing's a little bit off, but you get the idea of how much more detail there is over here with the comet than with the left-hand side. And then here's another one. This is one that surprised me. This is that cheap 50 millimeter 1.4 f1.4 lens. I think it's about 200 bucks from Nikon. And I had it out one night and I said 1.4, I'll try it on the stars, see what comes up. Just said, what the heck. The color aberrations are terrible, so you can see this blue halo around the stars, which obviously isn't there. That's something added by the cheap lens. But I think it's interesting how much clearer the right-hand image is than the left-hand image, right? This is one single image. This is a bunch of images, 12 images. Not that many, 6 seconds each, right? So a minute and a quarter, right? That's all the exposure time is, but it did come up with a lot more detail and cleaned up all that space between the stars. But if you're a real astro nerd, like I am, you already know that this is the Flame Nebula right here, right? This is with a cheap 50 millimeter lens, and this is the Horsehead Nebula. This is obviously a much better picture, but still, you know, I captured it with this cheap lens just saying, what the heck, let's see what happens. So I think it's kind of incredible how much detail you get on that right-hand side versus the left, right? Here's the Flame Nebula. You can't even tell that it's there, but it's amazing what that averaging can do. And then here's a similar comparison for using a panorama. The one on the left is my old Nikon camera, 24 megapixels. The one on the right is a 6-image panorama, so 2 columns of 3 images, just to make a really large image. So 47 megapixels, which is smaller than most of my Sonys, but again, I'll just zoom in to show an area for zoom. So you can see the noise that happens between the stars here and how much cleaner it is in the high ISO image. I'm sorry, high megapixel image. Yeah, so not much difference, just the image was enlarged and then compressed down. And when you compress it down, the noise just goes away. So a little more technical to make something like this, a little harder to put that together than using the software to just image stack. Image stack to me is the way to go. That's a much simpler way to go. So here's another 10-image panorama that I did up at Point au Barque Lighthouse, again, the thumb of Michigan in Lake Huron. This was probably a little bit too late at night. This was early in spring. So I probably went up there a little bit too late. You're starting to see sunrise here on the left-hand side, but it's a 10-image panorama. I learned a lot from this image and taking this image. This was an f2 lens, 24 millimeters, and I just panoramaed and did all the images together. Since then, I have a 14 millimeter f1.4 lens, so I was able to get much more detailed images of the same place. A little bit of distortion from the 14 millimeter, but it's a much better panorama. You can see some aurora here on the left-hand side of the image, and a distant town across Lake Huron into Ontario on the center area here. And of course, you can see the Milky Way arch much better because of the 14 f1.4 lens. And of course, the arch, we call this the arch of the Milky Way. The Milky Way is not arched, right? It's a straight line. So what the arch you're seeing here is really just a distortion from making the panorama from a wide angle lens. So the Milky Way itself is flat, right? It's a flat plate. We learned that from the slide 3, I think. But it looks like an arch when you do this sort of panorama that's probably 200 degrees wide, right? So it's a huge width on this wide angle compiled together with the panorama. Oops. Okay, next slide. So here's a quick slide to tell the difference between meteors, satellites, and aircraft. On the left side, aircraft have blinking lights, right? They go on and off, strobe lights. And they show as regular patterns in longer exposures. You'll see the pattern gets closer together as it's further away, but then it spreads apart as it gets closer. So this is an aircraft, looks almost the same brightness all the way through. Second one is a satellite, not blinking like an airplane, but it looks almost the same all the way through. A little bit of dimming here, but it's pretty much straight line dimming. There's no narrowing of the line, and it's pretty constant intensity. That's just reflection of sunlight back from a satellite to your eye, or to the camera in this case. The third one is a meteor, right? So meteors have kind of tapered ends to them, and are variable in intensity, right? As they burn up in the atmosphere or brighten in the atmosphere, they burn up, they get brighter and dimmer. And they do that fairly quickly, so they have kind of these tapered ends to them. Sometimes they'll actually have greenish color too. So here's three of those nemesis in one image. So this left-hand side is letter A is meteor, right? It was green, turned almost red here. This is 2 satellites. B is 2 satellites running in tandem, probably Starlink or something, running very close together. But you can see they're straight, non-blinking, running in parallel, pretty much the same intensity. They don't have a taper like this meteor has. And this one over here, it's hard to see a little bit, the strobing, but this is an airplane going from bottom left to upper right side. So, and there's another faint satellite through here too. I don't know if you can see that on the zoom, but they're there. So not everything's a meteor, but if you catch one, you catch one. That's great news. Hopefully you'll be able to identify that. Light painting. I want to talk briefly about that. Not my favorite subject because it's really hard to do. I don't like hard things. but sometimes a little exposure is better with light painting. I'll show some examples, some good examples, and not so good examples. Some people will use a blue hour exposure and combine that with a night sky image and just blend those together. That's called blue hour blending of an image. And it's definitely advanced class as far as Photoshop to blend those two images together and make it look presentable. So the biggest thing with light painting or trying to paint your subject with light is to only use it when the available light is not enough, right? So if you can't take a longer exposure and just gather the light that way, or there's just not enough light to light up that subject, maybe the moon is down and it's just a dark area. Just when ambient light's not enough, you can use light painting, but I would recommend against it unless you really know what you're doing. Add just a minimum amount of light. It shouldn't look like daylight. It should still look like night, something that's dark. So it shouldn't have a full range of color. Use whatever light you want to illuminate the foreground, preferably something with really even light. But whatever light you use should work. The more diffuse the light, the better it is. The brighter the light, the farther it will go. But sometimes it's difficult to light foregrounds and the ground itself. The real challenge is to light things evenly, right? A single light that you're holding in your hand doesn't light something that's far away as much as it lights something close up because of the inverse square law of light propagation. So something that's closer will have 4 times as much light as something that's further away. So it takes a lot of practice, a lot of work to get the light completely right. And you can experiment with times and patterns and how you illuminate it. Generally best to wash back and forth, so you try to even the light out back and forth, back and forth. More light on distant things and less light on foreground things. But you can play with angles. You can also play with colors too. You can do light modifiers. They can help with post-processing. You can either warm light to cool the light or diffusers to diffuse the light, whatever you want. And as I said before in the aperture discussion, you may want to blend a closer focused image of the foreground because closer objects may be out of focus if you have a really small aperture and you're focused on the distant stars. So it's a bit of a challenge. So in this one, we lit the barn, or this mill actually, across the river in West Virginia. And it worked out pretty well. Had to even it out quite a bit in Lightroom. And I believe, Bruce, we lit this barn up as well. And again, I had to even it out in Lightroom just to make it look a little more even. But I really want it to look like it's dark, right? That it's really dark outside. It's not daylight. This one's completely different. This was a worn stump of a tree buried in a sand dune on Lake Michigan. And I illuminated this stump, as you can see from the far left side, from the way the shadow is falling, with an orange filter on my light. And I just liked it because it really looks otherworldly, right? It looks like you're on Mars or something. So, but you can play with it, have fun with it. A real challenge. I don't remember if we lit up this tree or not, but I just have to say the processing a Milky Way image with tree branches is a real challenge with masking. So something to watch out for. It's really a difficult thing because the masking is difficult to get between all the little detailed branches. This one we lit up the foreground in this old grain elevator and the elevator itself. Not too bad, pretty even. But again, I had to even it out in post-processing. And then finally, here's a locomotive at twilight under the stars, eliminated by a flash setup. So they had set up flashes to freeze the motion. But I went with a longer exposure at twilight. So I ended up actually donating this image to the railroad And they used it on the visitor's guide next year, the next year, for that county. So it's kind of fun. I'll leave this in the YouTube presentation, or if you want to copy this, I can send it to you. I'm not going to talk about night sky processing of images, but I would highly recommend these two videos by Ian Norman of lonelyspec.com. I really learned a lot from these. There's a lot of little tricks that he uses for post-processing, one of which is to turn the saturation and the vibrance all the way up to get your color balance correct, and then turn them back down afterwards. So interestingly, I just saw somebody else do that with a landscape image, just to try to get the color balance correct. So interesting. Anyway, I'll leave these out here. So let's summarize. The equipment needed for wide field shooting: camera with manual settings, of course, sturdy tripod, remote shutter release or delay for shutter delay. I tend to use delay shutter. So when I press the button on my shutter, I let go of the camera. It delays 2 seconds and then shoots the image. So some people prefer a remote shutter release. I don't like to have to wire the batteries or any of that stuff. So, or hook it to my phone or anything, right? I just press delay shutter. I'm good to go. Widest, fastest lens you have, the fastest wide lens you have. So again, I talked about this before, recommended for astro work. Make sure that the lens, that somebody's used it, that somebody recommends it. I really recommend something f2.8 or wider, or faster, however you want to explain it, in the 12 to 25 focal range, depending on what you want to shoot. Again, lower is generally better if you want to get the wide Milky Way sky. If you go out at night, warm clothes, even in nights like this, hand warmers, foot warmers, leg warmers, whatever you need. Because it's amazing when you're standing out there at night behind your tripod how cool things can get, especially if there's some dampness in the air or a little breeze. It's easy to get cooled out there. Also good to keep your batteries inside your jacket or your coat to keep them warm as well. A dim flashlight, preferably with a red filter. Lights for light painting if you want to do that, ideally with variable intensity and color. Spare batteries. Oh, here's where I say it. Cold batteries die faster. Keep them inside your coat to keep them warm. And then optional, if you're crazy enough to shoot in the middle of the night when it's frosty outside, you can actually put a dew heater or a band of heating that goes around the end of your lens, around the objective side of your lens. Or you can put hand warmers with rubber bands around the lens to help warm it up and try to combat dew formation or frost. I've actually had frost on my lens sometimes. And then the recipe for night sky. Here's the recipe for success. I won't go through all these. It's just a summary of what we've already talked about. Using photo pills, clear outside. Preferably get set up in the daylight too after you travel to your location. I don't know if I mentioned turn vibration reduction or image stabilization off on a tripod. Generally, every camera is a little bit different. Set your camera to manual mode, manual focus. I turn auto ISO off. Yeah. Yeah, and then delay timer. So I think I've hit on everything else. I think I went through this one already. Again, yeah, we did. This is PhotoPills. It's a great app for planning Milky Way shots. So here I am planning a shot. The Milky Way is going to be the core is going to be to the southwest-ish, a little bit west. It's going to be visible from 9:40 to 12:18 a.m. So this is probably a fall shot. Gets up to 16 degrees above the horizon. Yeah, pretty easy to tell that from here. So it's a great app for planning a shot. Oh, it's the same one. Okay. And then have fun with it. This is that Sigma f1.4 lens, 14 millimeter. I really resisted buying one for a really long time because I already had a 14 millimeter lens that was f2.8, but the extra 2 stops of light are just tremendous in what light gathering capabilities you can get. You can see a lot of pink color in here, which is the nebulas up in the in the Milky Way, a lot of detail, almost too much light. Andromeda down here to the lower right. Down here's Orion. So it's amazing how a fast lens can really gather light. This one's Durango, Colorado. Unfortunately, the clouds didn't cooperate, but I was able to get a night sky shot over a reservoir. Not bad. And then these were I took in Great Smoky Mountain National Park of a comet from 2024. So up on top of Klingman's Dome on the left side, and then a lookout on the right-hand side, just past Townsend. The one on the right-hand side was a lot higher. ISO wasn't as clear at night, but the one on the left up at Klingman's Dome was, or Kauai Peak as it's called now, was a lot nicer, a lot better resolution of the Milky Way. And I kind of ended up giving a night photography class while I was there. There were so many people shooting there at the same time. But this is another place where I was in the parking lot, so a lot of cars were coming through the parking lot leaving, and they were washing their lights all across these trees, so I had to wait for the right moment to not get the trees in those headlamps. This is not the best image on the left, but it was a real challenge because I was shooting, this is actually Michigan's Capitol building. I wanted to shoot the comet right there by the Capitol building. And it was really hard because I'm in the city of Lansing, and I couldn't actually see any stars. So I had to test shot until I could find the comet looking over the Capitol building. But I finally did do it. Not a great shot, but it was just fun to execute, fun to try. And the one on the right is just north of Lansing and the lake, Kent Lake. Oh no, Kensington. This is Kensington, sorry. A few other comet shots. I really like to do those. They're a lot of fun. Not deep sky. I mean, these are done with just normal lenses, no tracking. The next one's, however, are done with tracking. So this one, I actually had a tracker on my tripod, so it's rotating as the Earth rotates to get these images. This is obviously the Rosette Nebula, deep sky images. I said I wasn't going to talk about deep sky, but too bad. Pleiades on the left and the North American Nebula on the right. Unfortunately, I just sold the lens that I took these with, so I don't know what I'm going to do. And then one more, something I wanted to shoot for the really longest time. And it's not the greatest image, but Andromeda Galaxy. Yeah, fun stuff. And this one's really interesting. This is not well known outside the astronomical community. This is called the Markarian chain of galaxies. And basically every smudge you see here is another galaxy of, 100 billion stars or something. So every little smudge here is yet completely another galaxy. So I went through and identified as many as I could in this image. There's more out there, but and then on the right, it tells you how far the distance is. So this one right here is 126 million light years away. So it took 126 million years for that light to be received by my camera. So kind of fun. Any questions?
What's your opinion of locking the mirror up for the mirrored cameras?
Oh gosh, yeah, it makes a lot of sense.
I mean, I've read both sides of it, but I just want to kind of figure that out. If what you're
Yeah, it's been a long time since I used a DSLR. Yeah, I would lock it up. It makes sense.
Okay.
Why would you
Yeah.
not do it? I guess. What's the argument
Right.
against that?
Right, understood. Yeah, I was
Yeah,
thinking the same thing, but
Yeah, it's just vibration, right?
yep,
Yeah.
exactly.
It
Okay.
dampens pretty quickly if you have a good tripod, but yeah. So yeah, interesting question.
Mhm.
So quick message from our sponsor. I'm headed to Palouse in a couple of weeks, and the busy time begins out to Pittsburgh and Newfoundland and Kodiak. So take a look at my 2026 workshops. Let me know if you have any interest. I'm starting to work on the 2027 schedule, which will be a little bit less aggressive than this year. But everyone's a place that I really want to go back to. The same with these two. They're all places I really want to go back to. So hopefully you consider joining me. So if you have any questions, send me a note, send me an email. You should have my phone number as well. Take a text message, whatever. Oh, I lost. I lost the Zoom. Ah, there we are. Okay.
Thanks, Scott.
Okay, you're welcome. Any questions? I stopped the recording.